Hi guys, I've missed you. We're gonna do volumes of revolution, and this is called the washer method. So not like your dishwasher, um, or your clothes washer, or your car washer, a washer like this. So the reason being is what we've been doing so far is discs, because what we've been doing, we've been taking a function like this, right, from A to B, and we've been rotating it about the axis, right? And when we do that, that makes a disc. And we've been doing it about like the x-axis here and also the y-axis, right? So we've been doing it A and B. Let's say we've got a function like this, f of x, and we've also been rotating it about this y-axis, right? Oops. Okay, so we've been rotating that about this axis. Notice that when we take a slice here, either our horizontal slice here or our vertical slice, notice that that slice touches the axis of revolution. Touching axis of revolution. So that there's no space between the slice and the axis of revolution. Now, if you notice, what we're going to do is we're going to take two different functions and rotate that area around an axis of revolution. So something like this. Let's say we have f of x and g of x. And again, we still go from A to B. But now, notice, now I'm taking this area and I'm rotating it about this axis of revolution. And notice now we've got a space between our slice and our axis. There's a little space there. And that corresponds here to the hole in the washer, right? So this goes right here, and that distance from the center, the axis of revolution, up to that first function is the radius of that hole, right? And our slice is going to look like this now instead of just a disc. Same thing, same premise if we do a revolution about the y-axis and we have two different functions. It works exactly the same way. So you've got f of x and g of x, say, and we're taking an area from A to B and we're revolving it. Whoops. There we go. And we've got our slice here, but our slice has a space in between, right? We call that space, that's going to be one radius, right? So we call that space little r, little radius, little radius. And then the distance out to the edge, out to the top of the washer, that's going to be the big R here. This distance here is big R. So if we show that slice, you've got this slice here. When we take that slice and revolve it, you're going to get this washer shape. Now, some people call it a donut. It's not actually a donut because it doesn't have a thickness, right, of a donut. Donut has, a nice round shape to it. So here, this distance here, this is our axis of revolution here, and this distance out, this is that space, that little r, and the distance out to the edge, that would be the big R. And of course, this thickness here, again, it's a little bit of the x-axis, so it's a dx slice. Okay, so in general, the volume of a washer is the volume of the whole disc, and then we're going to subtract out the space, right? So we've got the volume of the disc, that outer disc, this distance, the big R, minus the distance of the hole, or the volume of the hole. There we go. So volume of the washer, we already know volume of disc is pi r squared, and the volume of the hole will be pi little r squared, because that's little r is for the space, and big R is for that whole distance from here up to here. So what they do in the textbooks, they factor out that common factor, which is pi, and you'll see it this way: pi times big R squared minus little r squared. And then we've got the thickness, right? So the volume has this base area times the thickness, which is dx, or sometimes dy, but we'll call it dx today. Okay, so then the total volume is, we've got to sum, right? We've got to sum, all these washers are going to be stacked up along here from A to B, and then we just sum them up. We do that with our integral, A to B, pi big R squared minus little r squared dx. All right, let's do an example now. Now for the fun part, right? Okay, so we're going to find the volume formed by rotating the area. Example 1. Find volume formed by rotating area bounded by f of x is equal to root x, and g of x is equal to x squared. And we are going to rotate that about the x-axis. Okay, so I'm going to follow the same steps that we've been following all along when we've been doing volumes of revolution. So first we're going to do the sketch in 2D sketch. So here we go. Quick sketch. We know what root x looks like this. And our x squared, that's root x. And our x squared goes up like this, a nice parabola shape. X squared. Okay, and we're going to take this area and we're going to rotate that about the x-axis. Right? Okay, so if you'll notice, we do our slice here, and you guys can see we've got this little space here. This is R, and our big R goes all the way up to that top of the slice. Big R. Okay. Again, we're going to sketch the solid. Remember, it's okay if you're not an artist. It's fine. What I do is I take this part here and I sketch the outer. So I'll go, okay, well, I know what that looks like. That kind of looks like that. And then I'll reflect it over my axis of revolution. And then I'll draw the circles, right? And then I'll go ahead and do the inside. Now I know the inside is looking like this, so I know it starts at the axis of revolution and goes up like this. And then it reflects over. So you can kind of see that inside kind of has that nice, like a teardrop shape, and the outside looks like a, I don't know, a planter pot or something. All right, and then we know if we take a slice of this, we're going to have some solid and we're going to have some space. So our slice, our labeled slice here is going to be a washer instead of that disc. And we're doing it in the x direction. We're taking those slices in the x direction. So our width is the dx. Our little r here, little r, goes from the axis of revolution up to that first function, and that first function is x squared. So little r equals x squared, and big R goes from the axis of revolution, or the x-axis, up to root x. Okay, and then our last step is the integral. And you guys can't see that, so I'm going to move the paper up a little bit. Here we go, our integral. And we're probably going to need some more space, so we'll put that there. Okay. Oh, you guys couldn't see my sketch. I apologize about that. Sorry about that. Okay. Now you can see the 2D sketch. Okay. I'm really sorry about that. All right, and then my volume is equal to, oh, we need bounds. So our bounds are here, and then x squared equals root x, also at 0 and at 1. And we've done those problems before, so I think that's pretty straightforward. Okay, 0 to 1, and we go pi, big R squared, which is root x squared minus x squared dx. Okay, and then we can simplify it. So volume equals the integral of 0 to 1 pi. The square root of x squared is just x, and then x squared squared is x to the 4th dx. And now we can antiderive it. So pi times x squared over 2 minus x to the 5th over 5, and that's going to go from 0 to 1. So then that's pi times 1 squared over 2 minus 1 to the 5th over 5, minus, we can leave the pi out there, 0, right? 0 over 2 squared minus 0 to the 5th squared, or 5th to the 5th, 0 to the 5th over 5, and that goes to 0, obviously. So we get 1/5, or 1/2 minus 1/5. Well, 1/2 is 5/10, and 1/5 is 2/10. So we get 3/10 pi, or 3 pi over 10, and that would be your answer. Okay? All right, you guys, good luck. I think that's all I have. So this is for 6.2C. Hope it goes okay. Bye, guys.